Hey everyone, welcome to another deep dive. This time we're turning up the heat a bit, focusing on heat transfer engineering.
Yeah, lots of cool stuff to dive into.
I know, right?
Yeah.
Especially with these notes from TamTam and all the stuff you sent me. I've been thinking about if you had to design a super efficient cooling system for something powerful,
Oh, yeah.
like a computer or a giant data center.
That's a great example. And to do that right, you need to understand the basics.
For sure.
How does heat actually move around? There are three main ways: conduction,
Okay.
convection, and radiation.
Okay, so conduction, like touching a hot stove.
Exactly.
That direct transfer, ouch.
Yeah.
Convection is more about fluids like wind chill on a breezy day.
Right. Or a radiator warming up a room.
Exactly. And then radiation is the sun's warmth, even though it's so far away.
Millions of miles away, traveling as electromagnetic waves.
It can even move through the vacuum of space.
It can.
Wow, that's crazy. Okay, but let's focus on something specific that stood out to me in TamTam's work: condensation.
Oh, yeah.
Like dewdrops forming.
Condensation, it's like the opposite of boiling
Right.
gas to a liquid like steam becoming water droplets on a cold window.
Yeah, exactly. And here's where it gets interesting. TamTam mentions that when a gas condenses, it releases what's called latent heat.
Hmm.
It's like energy that was stored in the gas.
Right, and now it has to go somewhere.
So it moves through conduction and convection.
Exactly.
That's so important for designing things like efficient cooling systems.
It is.
Makes sense. Now, TamTam also breaks down condensation into two main types. Film condensation, where the condensing vapor forms a continuous film of liquid on a cool surface,
Okay,
kind of like a sheet of water flowing down a window pane.
I see.
And then there's dropwise condensation, where you get these tiny droplets instead of that smooth film.
Great, like on a raincoat.
Yes,
Water beads up.
it's all about how the liquid interacts with the surface.
It is.
Now, TamTam actually found that dropwise condensation is generally much more efficient at transferring heat than film condensation.
Interesting.
Why is that?
Well, you see, liquid isn't that great at conducting heat.
Okay.
So in film condensation, that smooth layer of liquid acts like an insulator. It slows down how quickly the heat can move away from the vapor.
Oh, so it's like an extra blanket on a cold night.
Mhm.
It's trapping the heat in.
Exactly.
But with dropwise condensation, those little droplets,
Yeah.
they allow for more contact between the hot vapor and the cool surface.
Right, much faster heat transfer.
Oh, so it's like the superhero of cooling.
Uh-huh.
I noticed TamTam also went into some pretty serious math to figure out how thick that liquid film gets in film condensation.
Okay.
There were equations and all sorts of variables.
You don't have to be a math whiz to get it.
Okay, good, because I'm not.
TamTam used something called Nusselt analysis to simplify those complex equations.
Okay, so it's like a shortcut.
Yeah, a way to make the math more manageable.
I like that.
By simplifying things, TamTam figured out a way to calculate the thickness of that liquid film based on things like the temperature difference between the vapor and the cooling surface and some properties of the liquid itself.
So TamTam basically created a roadmap for us to understand how thick that liquid layer will be. But why is knowing the thickness so important?
Well, think of it this way. A thicker liquid film means it's harder for that heat to escape.
Oh, right, like that blanket analogy again?
Exactly. So if you're designing a cooling system, you want to make that film as thin as possible
Makes sense.
to maximize heat transfer.
So knowing the thickness helps engineers create more efficient cooling systems.
For all sorts of things, power plants, our laptops, you name it.
This is so cool.
Yeah, it all comes back to understanding these basic principles.
This is fascinating. I want to learn more about these different types of condensation and how they're being used in the real world.
Let's do it. We can dive deeper into TamTam's research and see what else we find.
So we talked about condensation, but TamTam also goes into boiling, which is like the flip side.
Yeah, that
This is another big part of heat transfer, and it's everywhere, right?
Oh, yeah. Think about it. We cook with it. Power plants use it. Even our bodies use it to regulate temperature.
That's right. TamTam actually breaks down boiling into different types based on how much heat is being applied and the temperature. They mentioned nuclear boiling, transition boiling, and film boiling.
Okay, so imagine you're heating a pot of water on the stove.
Okay.
At first, you see those tiny bubbles forming at the bottom.
Yeah.
That's nucleate boiling, and it's really efficient for transferring heat.
So those bubbles are like little heat transporters.
Exactly. They carry the heat away from the surface.
That's a great way to picture it. So what happens when the temperature keeps going up?
Well, things get a little wilder. We transition into transition boiling.
Okay.
It's a mix of nucleate boiling and something called film boiling.
Film boiling, is that related to that liquid film we talked about with condensation?
It is in film boiling a layer of vapor forms
Okay.
between the hot surface and the liquid.
Interesting.
Like when you see a water droplet dancing on a hot pan. It's levitating on a thin film of steam. But here's the thing. Vapor is a terrible heat conductor.
So it's like that blanket again, but this time it's blocking the heat from getting to the liquid.
Exactly. Film boiling really slows down heat transfer, which isn't good if you're trying to heat something up.
So engineers would want to avoid that if they could.
In most cases, yes. And this brings us to heat exchangers.
Those things that help transfer heat between different fluids, but they don't actually mix.
Right. They're essential in tons of things. Power plants, refrigerators, you name it.
Yeah, but how do they actually work?
Okay. So you have a hot fluid and a cold fluid.
Okay.
You want to move heat from the hot one to the cold one.
Right.
A heat exchanger makes that happen without them directly touching.
Got it. Now, TamTam mentions all these different types of heat exchangers, like shell and tube, double pipe and fin and tube.
Mm-hmm.
Do they all do the same thing?
They all transfer heat between fluids, but their designs are different, which makes them better for certain situations. Like a shell and tube heat exchanger is super common. One fluid goes through tubes surrounded by a shell where the other fluid flows.
So if you were cooling a power plant, you might use a shell and tube heat exchanger.
Yeah, to transfer heat from the hot water to cooler water.
Makes sense. And what about those double pipe ones?
Those are basically one pipe inside another.
Okay.
Good for high-pressure situations.
And fin and tube designs, those are in air conditioners, right?
Right. The fins are like metal extensions that increase surface area.
Oh, clever.
Great for transferring heat to or from the air.
Okay, so TamTam also mentions different ways that fluids can flow through these exchangers, like parallel flow and counterflow.
Yeah.
What's the difference?
In parallel flow, they move in the same direction.
Okay.
Counterflow, they go in opposite directions.
Counterflow is more efficient.
Generally, yes.
Why is that?
The temperature difference between the fluids stays more consistent in counterflow.
Okay.
So you get better heat transfer.
So that's all about that temperature difference. This is fascinating. So many factors to think about.
There are, and TamTam's research really highlights how much goes into understanding heat transfer.
Absolutely. It's not just theory. It's about solving real problems.
Exactly.
Speaking of real problems, I want to go back to TamTam's work on condensation, that difference between film and drop ice condensation.
Mm-hmm.
We know drop ice condensation is more efficient, but what are the challenges in actually using it? It's a great question, and it really gets at why this stuff is so fascinating. You know, it's not just the theory, it's about actually using it.
Right, finding practical solutions.
Exactly.
Yeah.
One of the big challenges with dropwise condensation is you need those special surfaces to prevent the film from forming.
We need surfaces that are like those fancy raincoats.
Right.
That make the water beat up.
Exactly.
Yeah.
TamTam found all these methods like coatings and surface texturing, even materials that are naturally water repellent. But those treatments can be expensive, or they might not last that long.
Yeah, or they might not work with certain fluids or under certain conditions.
It's like a trade-off, right?
Right.
You want the efficiency of dropwise condensation,
Right.
but you need something durable and cost-effective and adaptable.
You hit the nail on the head. It's about balancing all those factors, efficiency, cost, durability, so many things,
Yeah.
to get a system that really works for a specific need, and that's what makes it so interesting.
I'm curious, are there any other areas where heat transfer is like super important that we haven't even touched on?
Oh, tons. Electronics, cooling for sure.
Okay.
As our devices get smaller and more powerful, managing that heat is huge.
Right.
If they overheat, you get performance issues, shorter lifespan, they can even just die.
So those tiny fans in our laptops and phones are working overtime?
They are.
What about for larger scale electronics like data centers?
Oh, that's a whole other level as we move toward even more powerful technologies. AI, high-performance computing heat transfer, is critical.
Wow.
We need totally new cooling solutions.
That can handle all that heat.
Yeah, it's a constant race to keep up.
Sounds like it.
But it's also super exciting. There's so much potential for innovation and breakthroughs.
This has been an awesome deep dive.
It has.
Huge thanks to TamTam for all their research. It really got us thinking.
For sure.
We hope you enjoyed it and learned something new about the world of heat transfer and how it impacts us every day.
There's always more to learn. So keep those minds curious and stay tuned for another deep dive into the world of knowledge.